Hi everyone. So for context, I'm a fourth year med student at Queens. So yeah, without further ado, let's get started. Ricky, do you want to go to the next slide? Great. So first of all, some disclaimers. Thank you to the UBC Biomedical Imaging Artificial Intelligence Research Cluster for funding. And this workshop is hosted by the UBC and Queens Artificial Intelligence and Medicine Student Societies. And before diving into it, I'd like to give a land acknowledgement. Queen's University is situated on the territory of the Haudenosaunee and Anishinaabe people, and UBC is situated on the traditional ancestral and unceded territory of the Musqueam people. So first, starting with the objective of this workshop. So the goal of this workshop is generally for medical students to feel comfortable both reading about and working with AI. And to sum that up in 3 points, we want medical students attending this workshop to learn how to analyze an AI application in healthcare, understand how to discuss AI literature in medicine, and know how to guide further AI training, be it like a student, like a summer studentship that you're working on, or just a research project that you have interest on your own. So before we started the survey, before we started the workshop, we sent out a survey, and from our registrants, we found that people are generally interested in 3 different roles involved in AI. So the first one is a user of AI. So this would be, say, a medical student, a resident, or a physician, someone who helps analyze AI. So this could be a physician working with engineers or a healthcare analyst. And lastly, a pure engineering roles or someone who helps develop these AI applications. All of these roles require AI literacy, and an example we like to talk about is, for example, with CT scanners. When they were first invented, it was a very new technology. Not very many people understood the principles behind CT scanners, but nowadays everyone from a medical student to a physician knows when to use a CT scanner, when to order a CT scan, the limitations of it and its strengths. So this workshop is focused on the first 2 roles, so the role as an analyst and the role as a user. But if anyone else has questions on math or computational questions, we're happy to go into detail about that, be it through questions that you guys ask during the session, or if you guys wanted to email us or message us separately. There are a lot of existing resources out there. I'm not sure if you guys have explored any of these different resources, but our point of view is that some of these resources, for instance, TED Talks were a little bit too simple in that they didn't really go into the principles behind these applications at all, while some were just way too mathematical based. For instance, a really famous CNN course at Stanford, which is a great course, but very math heavy. So the goal of this workshop is specifically for medical students. So we wanted to talk about it with a lot of breadth, to cover a lot of ground, but not too much into depth, and kind of glossing over the computing mathematics part a little bit, but diving into that a little bit more than, say, like a TED Talk. By the end of this workshop, all these buzzwords that, some of you guys may have heard before, talking to each other or have heard listening to different talks. We want you guys to understand what these buzzwords mean, be able to use them, and be able to understand what they mean in literature as well. One of the important ones here I like to highlight is cross-validation. This is very important in validating studies related to artificial intelligence. So quickly going over logistics, this workshop will be in 4 sessions. This is the first one. So with each session, it'll be about 20 minutes of presentation, 15 minutes of programming, and then 15 minutes of examples. All of the information, slides, as well as the actual workshop sessions are recorded, and all the info is on our website. Each session is on Wednesday from, that's a typo, it's from 8 to 9 p.m. EST, and feel free to contact us through email. There's no mandatory tests there's no mandatory tests or participation. We want everyone to learn at your own pace, but feel free to ask any questions. And there is a possible AEP component coming for students at Queens as well. So to quickly go over our instructors, so everyone that's teaching these sessions have either graduate research or professional software engineering experience. And without further ado, I say that a lot, so I'm handing it over to Ricky.
All right, so I'm the person on the left. So I'll be covering over some simple concepts of AI, some definitions and some myths, because we see a lot of AI buzzwords in the media, and we hope everyone will eventually be literate enough to know what is real and what is not. So for instance, we have to first go through some boring definitions. I know it's a little bit boring, but we want to start on the same playing field. So the definition of AI is a lot of people don't know the specific definition of AI. In the very basic fundamental level, AI is any sort of machine or program that can analyze environment and complete a task in an intelligent manner. So this last part, exhibit natural intelligence, is a total enigma. No one knows what the exact definition really means, because this comes from something called the AI effect in philosophy and sociology, where easy tasks that we thought were AI in the past aren't really intelligent anymore. For instance, early on, people thought vending machines were AI because you understand what the customer wants by pressing a few keys. But now we think that's a bit too simple. Now, character recognition, early versions of Siri or butter passing robots are not really considered AI anymore. So this is still a subject philosophical debate. But for all intents and purposes, we are going to say AI is anything that can sense an environment and complete a task. So these are some buzzwords you also might recognize. Artificial intelligence, we already defined that. Machine learning is a specific subset of artificial intelligence where the AI system will perform some tasks and then learn from its mistakes and then improve itself. For instance, an AI robot that's not machine learning will learn how to shoot a basketball in the net by calculating the trajectory and the wind and the weight of the basketball. A machine learning application will shoot the basketball, see how far it missed, and then readjust to shoot the basketball again. Now, deep learning is another buzzword. This is a subset of machine learning where the model you're building the machine learning application on has a lot of intermediate layers, a lot of intermediate math that usually no one cares to understand, but it works. So these are the buzzwords you hear, but they're all under the same umbrella of AI. So there's several misconceptions we want to discuss. Part of this is motivating everyone to know that AI is not really scary. It's something that is tangible and understandable and quite powerful if we understand it properly. There's a misconception that AI does not need humans, that we build an AI, they'll go in the hospital and they'll do the work of a doctor. This is completely untrue at the moment. Right now, there are no completely unsupervised AI systems in places that perform high stakes tasks like surgery or even diagnosis of patients, at least not in Canada. So, and what the majority of what we do in research is actually just using existing libraries and performing advanced statistics, which you will learn later. So there's another misconception that AI is objective. You remove the human component from it. This is also not true. So AI does remove subjectivity a bit by making things more quantitative. For instance, you're not relying on a subjective interpretation of a chest X-ray anymore. You're relying on quantifiable texture of the X-ray. But the way we program AI, we design the constraints to program the model. So because it's human design, there'll be human bias in the AI. The point I'm making is that there will be no AI judges in courts anytime soon. The last misconception is that AI can just figure out your data. You just give it some data, AI will figure out and do something amazing with it. This is not true. So this is a picture from the last season of Westworld, which was not very good, but had an AI that was completely autonomous, that judges people and figures out everything about you just by looking at your data. This is not true. Right now, AI is still very, very constrained. We need to design, when we design AI applications, we need to define what the AI application is for, the input data and the output data type, which you'll see in an example. So now, okay, all these misconceptions exist. Why do we still use AI? Well, AI is still faster than humans. Computers can compute simple tasks faster than humans, and we can do it automatically. So we can remove some of the manual labor. Sometimes we have greater accuracy than humans. But what's very interesting to me is that when AI analyzes some sort of problem, it usually looks at new complexities that will help humans. And this is just a figure showing how much money is put into AI. So, and this is up until 2019. So when you go to extrapolate to 2021, it's more of an exponential growth. So what exactly do I mean by greater complexity? So I'll give you an example. When chess AIs first started, the chess AI, they weren't very good until they went against Garry Kasparov in the 90s. The AI defeated Garry Kasparov. So everyone thought, okay, this is AI, great. This is AI taking over humans. But that's not exactly what happened, because what happened next was that humans in the next generation of chess players like Magnus Carlsen, now when they play chess, they use AI to analyze their games. And they use the AI to see what moves were better that humans did not see before. For instance, for those of you who are familiar with chess, maybe you'll go for early queen sacrifice, and that'll lead to a much better position against your opponent. So this reveals new insights about the data that humans did not know before. And as a result, this improves humans. And then now when we program new chess applications, we actually use human input, such as from Magnus Carlsen, who's current world champion, to build new AI applications that are better than the previous AI applications. So in this way, AI improves humans and humans improve AI. One caveat is that chess is a much, much simpler problem than medical problems. So in chess, no human can be an AI right now. But in medicine, AI has not taken over humans yet, which is what we will touch on very shortly. So now the question is, when should we use AI? So you should use AI when your data has some sort of complex pattern or signal that you think can be quantified. So for instance, if in this chart, we're trying to find a relationship between the days it takes to stop smoking compared to a patient's weight. And there is some pattern there. It looks linear, but it might not necessarily be. But the fact that there is some relationship we can extract out of it means there's a signal. That's a technical term we use, we throw around all the time. When we test an AI on a data set, we want to test if there is a signal or not. And then we want to use this data to complete some sort of difficult task, like predicting outcome, predicting days survival, predicting days until the patient stops smoking. So you should not use AI when there is no pattern or there is no signal, right? If you're trying to predict the days it takes to stop smoking by the number of windows someone has in their house, you might not get a signal from that, and you don't want to force a signal with that. That might lead to something called overfitting, which we'll touch into later. When the pattern is very, very simple, you don't need AI. You can do it with a simple linear regression, simple linear sum squares fit. You also don't want to use AI when there's very, very limited data, because AI requires a lot of information in order to learn, especially complex relationships between the variables. So this is an example of something complex that AI can accomplish. So AI has taken slices of a CT scan, and from the CT scan, it creates ultrasound images. So this is not a real ultrasound scan. This is the AI reproducing the ultrasound scan from the CT scan. So this is AI taking a complex problem with a lot of data, because this image is essentially a matrix of pixels from 0 to 255. So they're about, I think 5 million pixels here. And then you recreate something else. You can complete some complex task. We know there's a signal in there. We know that CT scans and ultrasound scans, they're somewhat related, but it's hard for humans to quantify. But this is something that AI could do. So now the question is that, okay, why not just leave this to engineers? Why do we need medical students? Well, medical students and future physicians are entrusted with analyzing a lot of medical information to know what's valid and what is not valid, and making those hard medical decisions. So I looked up COVID on Reddit in the search bar, and I looked up artificial intelligence, and I saw that there's a lot of articles that they sound very, very exciting, but when you open the article, first of all, a lot of them aren't scientific articles. And secondly, a lot of them are not validated. A lot of them aren't developed with best practices. So, but these are the articles that attract people. They're clickbait articles. So as a physician, you need to know how to filter through what is clickbait and what's not clickbait. So this is in 2019. Elon Musk said Tesla will have all self-driving car features by the end of the year. So we ran this workshop 3 times for context. And every single year I use this example because we still don't have self-driving cars yet. So there are flashy headlines that always appear everywhere. And of course, there are always buzzwords. So this was one I found online that really irked me. There's quantum information processing, machine learning, and quantum machine learning. So anyone that knows quantum mechanics knows that we don't know much about quantum mechanics. So using this as a buzzword to promote some sort of technology is not very valid. So when COVID happened, in the first 2 to 3 months, I think there are about 100 articles on artificial intelligence models claiming they're able to do something about COVID, claiming they're able to predict COVID based off a chest X-ray, based off a pulse oximetry, or based off just how the person feels. And then these authors, they did a full systematic review with the statistical due diligence and found that a lot of these articles were not good at all. They took maybe 50 patients, and then some of them got lucky with their AI algorithm. Some of them weren't that honest with the data. Some of them tested on they trained on their testing set, which is highly illegal in AI. So knowing what can go wrong in AI and the steps required to make AI go right is critical for anyone that needs to appraise AI in the future, such as physicians. Now, there is a tumultuous relationship between physicians and AI because a lot of physicians are worried that AI will replace physicians in the future. I showed the picture of the CT scan. That's something quite amazing. The question is, well, are we going to replace sonographers? Do we need sonographers anymore? Do we need radiologists anymore? So the big question that always pops up is, will AI replace physicians? And this is something that Zoe's an expert. She wrote a paper on this, so she'll discuss a bit on this.
Ricky's exaggerating a bit, but so will AI replace physicians? That is a very common question that sparks a lot of discussion among medical students. It's a very popular topic as well. So someone I like to talk about is Geoffrey Hinton. For those of you that know him, he is a computer scientist, a very famous one at University of Toronto. Some people call him the godfather of AI. In 2016, he very famously said that we should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists. It's now 2021, it's been 5 years. Evidently, AI has not replaced radiologists, and we are still training radiologists. And from our perspective, we don't really see AI replacing radiologists anytime soon. One of the main reasons we think of that is because of the infrastructure within the healthcare system. Simply put, the infrastructure just isn't there yet. A lot of hospitals still rely on paper records. For instance, me and Ricky were from Queens, and at our hospitals, it's very reliant on paper records. And at many other hospitals, even if there's much more integrated EMR use, there is still paper records that are used frequently in clinics and walk-in clinics or in the hospitals as well. And of the hospitals that don't use any paper records, what I'd like to talk about is EMR vendors. So there are currently 25 certified EMR vendors in Canada. There's even more that are certified in the States, and most hospitals use a variety of these products. There's very few hospitals, I don't know any personally, that only use one specific EMR product. In theory, these hospitals that use more EMR, don't use paper records, that should mean there's more data that's easily accessible for AI research. That's often not the case, because all of these products operate independently, and they almost operate in these silos where it's very difficult for them to talk to each other. It's almost harder to overcome that data barrier than if we were to just like write down all the data and then kind of like convert from paper to electronic. That's how difficult it can be to translate between these different EMR vendors. Another example is provincial data. So in Ontario, we have Connecting Ontario. There's a separate system that the name I forget in BC, but it's very difficult for people to connect between these two, even like provincially as well. Another issue is the actual data. Ricky, I'm not done with that slide yet. Another issue is with databases in AI. It's very hard to get data for AI training. Ricky kind of mentioned that when he was talking about the COVID-19 studies, but it's not just with COVID-19. You see a lot of studies in healthcare working with AI with less than 50 patients, even ones that have less than 10 patients. This seems almost a little bit silly when you think about studies in other fields where they would have, a lot more patients in order to prove that something is valid, but it's almost very commonplace in healthcare studies with AI. Part of the reason is because of the infrastructure, like I talked about, but there's also privacy concerns with provinces, with patients. There's restricted access limits, And right now, it's not as big of an issue, but I think that in the future, patient privacy concerns will also play a increasingly important role as well. Another barrier important to talk about is performance. There are currently AI products in the market, but they're rarely used because of their inconsistencies in their performance. If you're in the radiology department, you will see that there are certain protocols where you do have computers that will read the scans and provide you kind of their interpretation of what, area of ischemia, for instance. But oftentimes these results are not very reliable. And as physicians, humans, we kind of look at those results and just use them as a tool to help us in diagnosis. And a great example is, like Ricky mentioned, the COVID-19 pandemic. There was over 100 prediction models that were published in that time. The accuracy of these models ranged from 0.71 to 0.99 in terms of the area under the curve. However, another study that assessed these models found that none of them would be usable in a clinical setting. Another aspect to consider is regulation bodies like the FDA. It's very difficult right now for the FDA to assess AI products. These guidelines are always changing, and the existing ones, it's kind of unclear how good they are at evaluating a product's efficacy. So generally, their trend now is that AI products are being developed as physician assistant tools rather than physician replacements. And in our opinions, AI tools in the near future will hopefully make our lives as physicians easier and decrease the number of tedious tasks that we need to do rather than replace physicians. And the next slide just kind of, talks about the general opinion of key differences between AI and humans, basically. And from there, I'll give it back to Ricky to go on to the next section.
So
Can I ask a quick question?
Yeah, go ahead.
I actually discussed this with Ricky at one point, but there's a paper from DeepMind talking about analyzing retinal disease using some scans and a set of UNets, I think. And I was just wondering if you guys have read that, and do you have an opinion on that paper, its quality, etc.?
Yeah, I think that one was one of the first CE approved devices,
right,
for retinal scans. It's not standalone, so no regulatory body says that some non-physician can have it in their office and then just diagnose patients and bill for that diagnosis.
Right.
It still requires physician supervision. It works well, and it does some things that physicians cannot, such as looking at the texture that the UNet can by looking at the detailed down convolutions and up convolutions in that network. But you still need a physician to make that clinical correlation to it. So relevant to the last few slides, it doesn't replace a physician, but we think it's something that really enhances a physician's practice, we think.
I see. Okay.
Yeah. So that's actually a nice segue. We planned a question break. So if anyone had any more questions, feel free to ask or type in the chat. We're monitoring the chat. We'll take a 2-minute question break to see if anyone has any questions before we move on to some technical stuff. Okay, doesn't look like there are any. So
actually, I do have a question.
Yeah, go ahead.
I wanted to give other people a chance. Suppose you had your own medical practice and you had a bunch of data. Well, I mean, I'm guessing you can't just run that through your algorithms, even if you are the one that kind of like administers the data, right? You can't do that.
No, so there are ethical and regulatory pathways in order to use that data. The patients, in some cases, the patients have to consent for their data to be used that way. In some studies, the patient give a sort of a general consent that their data will be used for some research purposes, not necessarily AI. And then we can retrospectively say that, okay, now these patients have previously consented. Can we use their data for AI? So that's what we do in a lot of our studies. So, but if you're saying, can we just pick up any data that we recorded and use it for AI? The answer is generally no.
Because like what I was really referring to is like, suppose I don't know, I know a dentist or something, and then every time someone comes in, we do like, I don't know, a scan of their teeth or whatever, and then we give them a form and then say, okay, hey, yeah, do you consent to this? And they sign it. Is that legal? I'm just wondering.
Yeah. As long as they have the informed consent and they know
Right.
the risk of their data being stored and all the privacy concerns, that is considered informed consent, and then you can use those images. Of course, you still have to remove identifying information and everything, but yeah, that is a procedure that would be viable.
Oh, I see. Okay.
Yeah, so if you're thinking of asking your dentist for data, that's one way to do it.
Yeah. Well, it's just hard to get the data. I'm just wondering like how you could possibly
Yeah,
do
no,
it. Right.
that's actually a huge problem. Getting enough data and getting good data is especially for complex problems that don't appear very often.
Right. Okay.
Okay, so the next section we'll go over some. So I just made a slide in case I need to draw some technical definitions, because we're going to be reviewing a paper, and then I'll run through a really quick Python program showing how an engineer processes this data. So for instance, in this example, we have 5 hockey players. We want to predict who will have group A strep. Completely fictitious scenario. I'm just doing this just for demonstration purposes. So the definitions are, so these variables, for instance, the surname of the patient, the division they play in, their oral temperature, age, these are called, we call these features. So when we refer to features of some data set, it's sort of the categories of the variables. Each individual set of features is called an example or a sample. So for this player, the second player's set of features, this will be the second sample. So this is just to keep the language consistent. Some people call these variables. Variables is okay. Characteristics, please don't use that word. Descriptors, please don't use that word, because it's very confusing, because people use characteristics for 100 different things. Now this feature on the very right, so this is the thing that we want to predict. We usually call this the outcome or the ground truth. So something that we want to match the performance to. So now the reason there's a question that always comes up, which is, where does machine learning projects stand on the hierarchy of evidence? And why do we need machine learning? So a big reason is that we see that, so when I searched for COVID on social media, what I found was that, unfortunately, most of the articles always say something, expert's opinion. Some sentence, some claim, according to experts, something according to experts. And if you remember the hierarchy of evidence, expert opinion is on the very, very, very bottom, right? There are some scientific articles, but they're usually on the second or third page of Google search results, which no one ever looks at. So unfortunately, expert opinion has plagued social media everywhere, even if good scientific studies are available. So machine learning isn't a traditional control versus comparator study. It's not a randomized controlled trial. We take data, we try to make a predictor, something that can predict some outcome, and then we test it on the data. So it's not really, we don't really recruit patients. We do sort of separate and balance them, but it's after the fact they've been recruited. So, but it's not necessarily a cross-sectional case control study, because we look at the performance of the machine learning instead of looking just at a group of patients and what happens to them, and then computing some significance tests. So my claim is that most of the time it's between a randomized controlled trial and cohort studies in terms of strength of evidence, which means that if to validate a machine learning application, you need to go through a randomized controlled trial and then systematic review in order to externally validate it. So there are, now in statistical analysis, there are classically these descriptive statistics like mean, standard deviation, spread. There are inferential statistics, but there are also, what's really common is computing ANOVA or p-values. So when you compute a p-value, usually you have one group and a group where you have some intervention, and then you see the differences in outcome between the two groups. And then you compute a p-value. If p-value is under 0.05, that means they're significant. And that's usually what's packaged into a paper. So then machine learning doesn't really use p-values in this way, because the way we use p-values is we do a statistical test to say that there are differences between these two groups. But just saying that there's a difference, it's not really predictive, right? We can't use the p-value and then predict if a patient has this condition or this other condition, right? P-values are very, very useful. They're very, very good for finding useful features. When I say features, I mean the variables we're looking at. But p-values alone are not predictive. And machine learning instead does something slightly different. So this is a common score. This is the Curve 65 score. How this scoring chart was made was that they took features that the clinicians thought were relevant, such as if the patient's confused, if their urea is above a certain threshold, if their age is about 65. They found that these variables had high p-values of severe disease. And then they create this scoring system. They assign 1 point to each. If your point is within a certain range, you have a certain 30-day mortality. And this was externally validated afterwards. So there's some limitations. So this is great. This is easy. This is interpretable. This is used in clinics everywhere, right? When we're in the clinic, we have this on MD-Calc all the time. But the limitations is that first, they hand selected the variables that had a significant p-value, and then they assigned this like really nice rounded number. And we know that biology usually doesn't have nice rounded numbers. So we think we can improve on this and make our predictions a little bit better by having some complexity. So I'd like to bring your attention to this, this paper. I'm just going to open one moment. I'm just going to share this one interesting paper that uses machine learning, but a lot of people don't know that uses machine learning. In fact, I think a lot of schools show this paper in the end of first year. So this is the paper. So this is something called the PCARN trial, where they try to figure out a scoring system to look at CT scans and determine if a child has risk of traumatic injury or not. So at first glance, it looks like a well-conducted study. You know, they had 42,000 samples, and then they wanted to create a scoring system based off, you know, the age, the Glasgow Coma scale, whether they have hematoma, the mechanism of injury, to see if the patient is likely to have a traumatic brain injury. So this is in place. This was published in 2009, and it's actually standard in a lot of centers used in their radiology and emergency departments. So this scoring system is the way this is. So these are the features that they looked at. So for instance, whether they have mild, moderate, severe injury mechanism, their level of consciousness duration, their Glasgow Coma scale. And they took these, they first look at the p-values like most studies, and then they use this to build a scoring system. But the way they use it to build a scoring system is, if I scroll down to the methods, so I'll share this paper with everyone afterwards if they're interested, but I'll just highlight the pertinent components. So they use something called binary recursive partitioning. First of all, no one calls it that anymore. We call it a decision tree. CART is the specific algorithm for decision tree. And then they use 10-fold cross-validation. So that's a buzzword that came up from before. And standard Gini splitting rules. This is just extra detail on how the algorithm works. But essentially, this is machine learning. They used machine learning back in 2009 to make a head trauma CT scan scoring system to predict if patients are likely to have traumatic brain injury or not. So this is machine learning. They used machine learning 12 years ago, but not in the way you expect, right? They're not going to make a robot. They didn't use machine learning to make a robot in the emerge to look at patients and determine if they need a CT scan or not. No, instead, they use it for advanced statistics to build a scoring system similar to scoring systems everyone's used to. Right, so this is sort of the direction that a lot of machine learning is going towards, making better predictions using better statistics. Okay, back to the presentation. So this is the specific actual algorithm they came up with. So it's actually quite simple. You look at 7 different features and you determine if a CT scan is required or not. Right? They look at the variables or features, they train the machine learning model, and then they use a model to evaluate future patients. Now, this specific method they use is called a decision tree, where they put the features in these nodes, and then they give each node a threshold. For instance, this first node would be your GCS score. If your GCS is above a threshold of, say, 14, you go to the left side, otherwise you go to the right side. And then you keep going down each variable at each node until you reach a terminal node. And then that terminal node will tell you whether you're likely or unlikely to have traumatic brain injury. This is one of the more popular machine learning methods because it's very interpretable. It looks like a clinical flowchart. And this is one I actually recommend a lot of medical students use for their projects and their research because clinicians love it. it's usually quite high accuracies, especially with more modern methods, and it's quite easy to implement. So in the next few weeks, we hope that you'll learn the capabilities of AI. We'll show you lots of examples of things that work, things that don't work. Very important, know the best practices, how to essentially audit an AI application to say if someone, let's say a salesperson comes to you and says, hey, there's this AI technology, then hopefully you have enough knowledge to know where to start to validate if that AI technology is feasible or not, and how to work with AI in the future, whether you're collaborating with engineers or whether you want to be proficient in learning how to use the technology in your practice. Okay, so this ends the presentation part. We have some quick programming examples. So while I set it up, does anyone have any questions? Feel free to ask or type in the chat.
I actually had a question about the decision tree.
Yeah, go ahead.
So they generate those rules. Did they just find one decision tree? Like, did they use just a single decision tree, and they didn't do any of the random stuff and averaging? They just did one?
Yeah, they did one. So when they use a lot of different decision tree and they average it, I think that's the random forest method, which is more modern and actually much better. I mean, if I was reading that paper, I would say use random forest, don't use decision tree. So yeah, but it's also quite an outdated paper, so maybe that's why it got through.
Well, I just, I was just thinking like, oh, you use like the simplest possible thing that you can learn these days, and it worked, and it's doing well, and that's really cool.
Yeah. If it works and it's simple, like keep it simple.
Okay.
That's also a mantra of machine learning. So I sent a link to the online Jupyter notebook. I'll share my screen to show you what it looks like. So this is the programming example we prepared. So you can open the link and open it in your browser, or you can just watch me run through the code, whatever you want, whatever you think it's best for you. So we're going to show you how we process data and how we look at and audit the data. So first thing you have to do if you want to run this code, you have to go file and save a copy in your own drive, because the link I sent you is the master copy. So in order to run it, I think you have to save it in your own drive. But a quick boot camp on how to run this. So this is in the Python programming language. These are, when you click around, you see like these highlights. These are different cells. So when you run a cell, it'll only run the code within the cell. There's text-based cells. It's called Markdown. So it's just descriptions. This is not code. And then there is more, things that look like things hackers would do. Like this is the actual code. So when you run this, it has a run symbol on there. This will run the actual code. So the first thing to run the code, you either click the play symbol, or the shortcut is hold Control and press Enter, and that'll run the code. So in this example, we're going to load a data set, and we're going to look at some descriptive statistics and just visualize it and understand why we need machine learning. So first thing, so this is made by Prash, by the way. Most of this is made by Prash. So he's not here today, but he's the brains behind a lot of this programming. So I'm going to run this first block. This loads in some libraries that I will need. So libraries are existing code packages that we're going to leverage, so we don't have to write the code from scratch again. We're going to load a specific data set called the Wisconsin breast cancer data set. So I'm going to run this code. So anything in green these are called comments. So these won't run. These are just for mental notes for the programmers. This command loads the data set, and this next command will print out what's in the data set. So I'm going to run the cell, and we see that, okay, it printed a bunch of unintelligible, numbers, and then a bunch of words. Don't really know what this means. Well, if you do know this data type, they're printed out in arrays, so you sort of know what this means, but it's not very interpretable. So what we can do is this data set has a key called description. So when we ask the data set what its description is, it'll give us something more interpretable. So I'm going to run this next cell, and it's going to show us this data set. It has 569 samples. There are 30 features. They call them attributes. Like I said, this is a very old data set, so people use different words. And the features include the radius of a breast image, the texture, perimeter, area, smoothness, compactness, concavity. So essentially a lot of geometric measurements of a breast biopsy sample that they took an image afterwards. And then there's this outcome column, which is whether this breast mass was benign or malignant. So you can already start to see what sort of problem we're formulating. Maybe there's some way we can use these features to predict whether this lesion is malign or benign, benign or malignant. So, but you see, like these features, they're not really interpretable. I mean, radius, yeah, if a radius area is larger, more likely is malignant. But where exactly, what cutoff should we have, and how do we select a good cutoff that gives us good accuracy? So, fractal dimension, this is not that interpretable by humans, but maybe a machine learning program can interpret it. The rest is just some copyright information. So, we're going to load the data set. We're going to organize it into something called a data frame, which in Python just makes a nice table that we can work with. So this, I'm going to run this cell. So this loads the data set, and then it prints out the first few samples. So we see this is patient 0 to 4. In computer science, a lot of times they start counting from 0. Unless you're using MATLAB, then they start counting from 1, which always gives me a headache. Anyway, so we see all these features. Each patient has some value in that feature and some outcome label. Okay, now let's see if we can visualize it further. So this exercise is called exploratory data analysis, where we're not using any statistical analysis or machine learning yet. We're just trying to look at the data to see what sort of problems we can define. So here, let's plot two different features. We're going to plot radius compared to texture. So this will plot on the x-axis radius, on the y-axis mean texture. And we see that, and then we'll label the malignant and benign lesions with different colors. So 1 is benign and 0 is malignant. So the purple ones are malignant. So we see there's some sort of pattern. As expected, when things get larger in radius, they're more likely to be malignant. Maybe we can draw a line straight down here and separate the patients, but we're going to miss this group of patients that have malignant lesions.
Ricky, I don't see the graph.
You don't see the graph? Oh,
yeah, like I see you pointing, but I don't think it's sharing. Like it doesn't share the graph over your code or something.
Yeah, let me try. Thanks. Try sharing my screen again. Yeah, I think Zoom is. Okay. One moment. Okay. Okay. I will try sharing on this other computer very quickly. Oh, thank you. Yeah, screen's frozen. Okay. I'll share on this computer. Is this working?
I don't see anything. Oh, no, yeah, you're good, yeah.
Yeah. Okay. Sorry about that. Okay. Yeah, can you see this?
Yep.
Okay. So, so we load the data set. What was the last thing that you saw?
Just right before you started talking about, it looked like you were pointing to a graph, but
okay.
Just couldn't see the graph, that's all.
Great. Okay, so in this graph here, I'm going to plot radius compared to texture. The purple dots are the malignant lesions and the yellow ones are the benign ones. So if we look at radius, it looks like as you get larger in radius, you're malignant. So maybe we can draw a straight line down the middle around 15, but that would leave out all the patients who are malignant under 15. So that's not good. So texture is another interesting one. Texture doesn't look like there's any clear delineation. And we don't really know intuitively what texture means. But as we'll see later on, maybe if we combine these with other features, we can get some sort of high dimensional differentiator that can tell us if a lesion is malignant or not. So what we can do is we can visualize, the range of our data set to see if there's any outliers that we need to remove. So this section just prints out the minimum radius, maximum radius, this worst smoothness. And we see that well, there's the range of radius is from 6.9 to 28.11. That doesn't really mean anything, but we can compare the smoothness of benign tumors to malignant tumors. And there's some sort of differentiation. When you do this, you'll probably get okay p-value. But again, this is difficult. This is difficult to use. How do you make a scoring system based off this? What some people do is a linear correlation analysis, where you look at each variable and you see almost like the odds ratio. How does this variable differ from malignant patients to benign patients? So I'm going to run this cell. This builds. So I'm just using this library that's available. That's available as standard in the Python package. So this will print out a correlation matrix that'll show you the different features, and then it makes a heat map of how it's related to each other feature. So the one we're interested in is label. What's highly correlated and not really correlated with label? So yellow is highest correlation, dark blue is the worst. So if we look at all these features, a lot of them don't have really that great correlation, right? Maybe mean fractal dimension is highly correlated with label, but if we base off correlations and p-values alone, we start to see that we're likely not going to get a good predictor. And then we can visualize this numerically. So this is not a heat map. This will be the actual numbers. And what you could do is you can go through each one, find out what the maximum correlation ratio is, minimum correlation ratio, which parameter has the best correlation ratio. And we didn't do this because it will take a lot of time, but the spoiler is that if you base off of correlation ratios alone, you'll get a prediction accuracy of about 0.7, 0.72. With machine learning, in the next few weeks, you'll get an example with machine learning with exact same data set. Your accuracy will be about 0.9, 0.93. So this is an example where machine learning really helps look at complex relationships between data to achieve something that is quite remarkable. Now, again, this doesn't replace physicians, though. You still need to make that clinical correlation, assess if the patient has the symptoms consistent with malignancy in order to guide treatment. So this just gives you new tools for physicians to improve their practice. It's like a new medical imaging modality, for instance. CT scanners did not replace physicians, and AI likely won't replace physicians. So next few weeks, we'll run through more of these program examples. We'll go through some technical concepts of machine learning and how they relate to clinical problems. And you'll understand what machine learning can do and what it can't do. So that's all we have for today. At this point, are there any questions?
Hi, Ricky. I had a quick question about, you mentioned something about correlation ratios when we're looking at the features. Oh, what exactly is a correlation ratio?
Yeah, so by correlation ratio, I really mean the Pearson R correlation coefficient, which is it almost compares the scale of the values of one patient group to another patient group. It's almost like an odds ratio. It's like how much more of this value exists in malignant patients compared to benign patients. Does that answer the question?
Yeah, that does.
Yeah.
I was just confused about the ratio part, I guess.
Yeah.
Yeah, Michelle also responded in the chat too.
Yeah.
Ricky, you're muted.
Oh. Okay. Yeah, sorry, the Zoom is buggy on this computer. But yeah, if you have any questions, feel free to type in the chat. So there are some questions that were submitted. Some people ask about what the role of natural language processing is in medicine. So natural language processing is for using machine learning to understand understand text and interpret what it means. The most famous example is Watson in Jeopardy. There are applications where any situation where you want a human to interpret text or to generate text is an application for natural language processing. For instance, interpreting a patient report, interpreting a patient history. You can use natural language processing to try and extract something meaningful from that data. We'll have an example of that, I think, in 2 weeks, but there are definitely applications of NLP in medicine.
Also, for instance, when you're dictating a clinic note as a clinician or as a radiologist, you're dictating image report. Right now for dictation services, people manually translate those, but natural language processing could also be used for that as well.
All right. Yeah, we'll stay for like another 2 minutes, see if anyone has any questions. Also hope we quell some fears that AI is going to replace physicians. I think everyone will have a job in next few years.
Do you think the jobs of physicians will change though? Because, like, for example, I work on manufacturing assembly lines and stuff like that, and AI on that. And so, people's jobs, jobs that used to exist, such as like, inspecting, like manually inspecting different objects, that would go away. But it basically opens the door to other jobs that the workers do. So suppose that, you could have something, an AI that would get rid of some of the lower level, like simpler tasks that a doctor might do. Then perhaps like what other stuff would a doctor, or I mean, what are examples of something that could get much more efficient with AI? And with that saved time, what would a doctor do?
Yeah, so like you said, things that are considered low risk and almost manual labor, those are the first things on the block for AI to address. In radiology, for instance, image segmentation and view verification. When you take an ultrasound of a kidney, you try to look for where the maximal length is. And usually it takes a sonographer, a minute to go through and see where it is. But if you scan through and use an AI application, you can see where the maximum length is. It's not the worst if you get it slightly wrong, but it's something that AI could do. To answer your question, how would it change jobs? It will definitely change the type of data that physicians will have to interpret. The analogy we always use is like when MRI came out. Now physicians have to study MRI. It sort of it didn't replace, but it moved a lot of the training from a physical exam of your neurological symptoms to assess if you have a stroke or not. Instead of squeezing each finger and spending 30, 40 minutes with patient, like doctors still do that, but they also have to train in interpreting a CT scan and interpreting an MRI so that they have higher accuracy predictions of the diagnosis. So that's sort of the direction I see. Two major directions I see. Zoe, Michelle, do you have any input?
I think potentially a lot of things around maybe NLP, as we were talking about earlier, and making the use of EMRs a lot easier and more efficient. I spent the day actually with my PI, who's a clinician, and he spent a good 2 hours just entering and manually moving data around within his EMR for an arrhythmia clinic he runs here in BC.
Oh, wow. Okay.
Yeah, but it's definitely not as fast as in materials engineering or in computer engineering, because those are relatively lower risk tasks, and you can test them quite easily. You don't need live patients to test. So.
Okay. Are there any examples of AI that is like not used to make a decision, but it's kind of like an example of shadowing a doctor, where let's say the AI predicts something that's unknown to the doctor makes a decision, and then there's a comparison between them?
There's nothing I know of in practice. That's definitely, there are definitely active research in that, where, for instance, AI just interprets a CT scan. The doctor doesn't know much about how to interpret like texture of this organ, and the AI gives some sort of feature representation that is significant to some outcome. And then they work together with pathologists to take a biopsy of that tissue to see what the AI is learning. So
Oh, interesting. Okay.
yeah, it's an up and coming field, but yeah, nothing's in practice yet, as far as I know. Yeah, but anyway, so I think that's about time. So thanks everyone for coming. So next few weeks, Zoe, Michelle, and I will rotate teaching some specific technical concepts. So I'll have a lot more programming, a lot more examples. Everything is going to be updated via email and the website. So everything's going to be recorded. And thank you all for coming. And if you have any questions, feel free to ask us anytime. Otherwise, we'll see you all next week. All right.